Concept paper. I said this one is 42 October, November 20. So we're going to start with the same one. Now, starting with this lattice energy question, he's saying that calculate the value of the enthalpy change corresponding to the transformation, which is W. So we have to calculate this one. Okay, in this question, we have to calculate W. So let's quickly try and do that. Remember, one path is equal to the other path. So that means if I want to calculate W, I would have to go. I mean, that's by one path. So the other path would be going in the other direction. That would mean W is equal to. So W is equal to X plus Y and minus Z. So it's X plus Y minus Z. Okay, so one path is equal to the other path. So you could have made any two paths equivalent. It would have meant exactly the same thing. So what is X? First thing, what is X? Can anyone identify what X is out of these values? Which one is X? What do you call this thing? Munya, any idea, Brar, Bhaskar? What's X, Alicia? Elements forming calcium chloride solid.
Formation.
Okay, so that is formation. And the value of formation is given over here, that's minus 795. Okay, when elements form 1 mole of a substance, that's formation. What is Y then? A solid that's turning into aqueous. What is Y? Kya bana? What's Y? Solid turning into aqueous. What's Y? Munir, Saim, any idea? Umar?
Enthalpy change of
Solution. Okay. That is minus 83. 1 mole of a solid. That's given over here. 1 mole of a solid turns into 1 mole of aqueous. I said Z is lattice energy. Gaseous ions turning into solid. So that is lattice energy, and Z is what is lattice energy over here? Did they give us lattice energy? No, it's not lattice energy. What is Z? Z is not lattice energy. Gaseous ions turning into aqueous ions. What is that? Hydration. Okay, that is hydration. So the hydration of the ions, calcium ions, hydration is they gave us the hydration of Cl ions. That's minus 364. So this one is minus 364 times 2. Okay, so they gave us the hydration of Cl ions. So that's given, and into 2 because this is for 1 mole. What do you do for calcium then? That's not given. Calcium ions turning into aqueous. He's saying the energy shown can be used to calculate the enthalpy change of hydration of calcium ions. So he's saying calculate the value of the enthalpy change corresponding to the transformation W. W is definitely the negative of lattice energy. So the point is, this thing is not actually given. So that is X. That's not given. So you can't really calculate W as well because W is not known as well. He's saying, let me read the question. The energy cycle shown can be used along with suitable data to calculate the enthalpy change of hydration of calcium ions. Each arrow indicates transformation. Each transformation consists of 1 or more steps. So the following data is provided, and calculate the value of the enthalpy change corresponding to transformation W, showing your working. So this one is not about and use your data to calculate the value of the enthalpy change corresponding to transformation Z. So we can't use this set cycle to calculate W. That is impossible because 2 of the values are unknown. So we're going to calculate W separately. W is the lattice energy. So the confusion in this question is that we first thought that we were going to use this cycle to calculate W, but we can't do that because because there's a missing value which we don't have with us. So we're going to calculate W separately. How do you calculate lattice energy? You calculate lattice energy using the Bohr cycle. So what we're going to do is, remember, this one is not the Bohr cycle. Bohr cycle is not about solutions. So we're going to construct a Bohr cycle first. And we're going to try and calculate the lattice energy first. Using that. So what is the Bohr cycle? You can start with enthalpy of formation. Enthalpy of formation is, you've got Cl2 gas, and it turns into CaCl2 solid. That is delta HF. Now that value is given over here. What's the other path? The other path is that you atomize these elements. I mean, what if you want to do this stepwise? So the first part would be you atomize these elements, you turn calcium into gaseous atoms, and you turn Cl into gaseous atoms as well. So how do you turn calcium into gaseous atoms? The enthalpy of atomization of calcium is given, that's plus 193. So this value is provided, it's given over here, it's 193. Enthalpy of formation is given as well, that's minus 795. So this value is also given to this. Now this one is not just the enthalpy of atomization of calcium, it's also the atomization of Cl. And they did not give us the atomization of Cl. So how do you find the atomization of Cl? It's basically the breaking of the Cl-Cl bond. Cl2 turning into Cl atoms, you're breaking the Cl-Cl bond. So you can have a look at the data booklet. And from there, what you can do is you can use the bond energy table. So where is Cl? This is Cl242. So in the question, you're just breaking exactly 1 mole of Cl bonds. So that's 242 for that. Once you have atomized them, you're going to ionize them. So how do you ionize them? You turn calcium into 2+ gaseous ions. And in the same step, you can do the other one. Cl can gain the electrons and it can form a Cl-1 gaseous ion. So both things can happen in the same step. So calcium atoms losing 2 electrons, that is not given over here. So where do you find calcium atom losing 2 electrons? You look at the data booklet again, and in the data booklet, the first and the second ionization energies are provided. So calcium losing 2 electrons is 590 and 11. So that's 590 and 1150. So that's 590 and 11 and 1150. And then Cl gaining electrons. When Cl gains electrons, that is electron affinity. That is given over here. Electron affinity is the opposite of ionization energies. So that is given as minus 349. So this is Cl gaining an electron. So Cl atoms turning into Cl-1 ions. That is minus 349 into 2 because there are 2 Cls. And then the last step, that is what W was. Gaseous ions turning into a solid ionic lattice, that is lattice energy. ठीक है, so the confusion. हाँ.
See, हमने अभी calcium की ionization energy लिखी 590 और 1150. लेकिन for chlorine we wrote ये hydration की value. तो ये
नहीं, we didn't write hydration. We wrote electron affinity for Cl. Because Cl is not getting ionized. It's actually forming a negative ion. It's gaining electrons.
और दूसरा से ये what was the Bohr cycle? मतलब कि first we had to made it gaseous. ये क्या करना था सर?
नहीं, Bohr cycle had the following steps. Bohr cycle was, you can make a Bohr cycle out of pretty much anything. कि इसके ऊपर दिखा देता हूँ just a second. बासा ये question है.
Sir, after formation, we're getting calcium chloride as solid, but basically W, that leads us to like the ions, they're in gaseous form. So how are we bringing formation into this?
Need this thing?
Yes, we're getting calcium chloride as solid. But if you take a look at W, that's calcium ions in gaseous form and chlorine ions in gaseous form as well. So Where is calcium chloride solid?
Calcium ions in gaseous form. Acha, Waki, that's not even. Why did you not mention that before? Because that's obviously not the lattice energy. Is it the lattice energy? It is the lattice energy. No, it's not the lattice energy actually. Really sorry, it's not the lattice energy. We probably didn't have to do all of that. W is not the lattice energy because the definition of lattice energy is okay, you've got ions, gaseous ions turning into an ionic solid. Okay, Basga, you're right. This is definitely not the lattice energy. So when they had asked you to figure out what W was, what you just had to figure out was how do you turn calcium solid to calcium gaseous ions? So how do you turn Cl2 gas into Cl minus 1 ions? So this is the part W. How do you turn calcium solid to? So we just figured that out. This is what W is. That you have calcium solid. What are you going to do? You're going to atomize it first. You're going to turn it into a calcium gaseous atom. And once it has atomized, you're going to turn it into a calcium ion. So the whole complete Bondable cycle wasn't really necessary. These two things were not really necessary. This was the only part you had to figure out. This was W. Atomize and then turn it into ion. Cl2, same thing. You atomize, you break the Cl-Cl bond, you make it into an atom, and then you turn it into a Cl minus 1 ion. So what is this part, W? That's 193. So that's 193 plus 242. And when you ionize calcium, that's 590 plus 1150. And the last part is you make the Cl gain electrons. That's electron affinity. That's minus 349 into 2. Is that clear that this is W? You start at this point and you end at this point. And you have to be careful about the arrow direction as well. W was solid turning into gas. So that's fine. Solid turning into gaseous ions. So what do you get for this? Is this part clear? Bhaskar, is this clear now? Is this clear
Yes,
to everyone? Sign clear? Monia, is this clear? Bra.
वो हेबर साइकिल आप एक्सप्लेन कर देखिए क्या था.
I'll quickly explain. But in this case, you didn't need this thing. I mean, this thing wasn't really required. Maybe it's going to be required later, but not to calculate W. So I'm just going to talk about the Hess cycle, the Bond-Haber cycle very quickly. What the Bond-Haber cycle was, so this was what the Bond-Haber cycle was. That any ionic compound, it was only for ionic compounds, specifically for ionic compounds. And you take any ion, let's say NaCl, you start off, you can start off at any point. If you're doing a Hess cycle, you can start off at any point. I usually like to start off at the enthalpy of formation. So if I want to make NaCl, I'm going to take some Na and I'm going to take some chlorine. This is the enthalpy of formation. NaCl solid would be formed. And this is going to be half Cl2. So that's delta HF. So Bond-Haber cycle was, how would you do this stepwise? Your starting point is this one. And how are you going to do all of this in a stepwise manner? You start at this point and you're going to end at that point. So the steps were, first thing, you're going to atomize the sodium. And you're going to atomize the chlorine into chlorine atoms as well. So the first step was atomization. Once atoms are formed, you're going to ionize them. Na would be turned into Na plus 1 gaseous ion, and Cl would be turned into Cl minus 1 gaseous ions. So that's the second step. That's you ionize them. Once ions are formed, those ions will get together to form the solid ionic lattice, and that's your lattice energy. Now I've combined a couple of steps. Atomization will happen in 2 steps, like sodium will be atomized and Cl will be atomized. Like in this case, atomization, what would atomization really mean? Atomization would mean it would be the enthalpy change of atomization of sodium. Plus it would be the enthalpy of atomization of Cl atoms. But for Cl atoms, remember this, for molecules, covalent molecules, atomization can be found out using bond energies. Because all you're doing to form atoms is breaking the Cl-Cl bond. So this is for gaseous covalent molecules. So if your element is a gaseous covalent molecule, all you have to do is, like if you want to form oxygen atoms, all you have to do is you take the oxygen molecule and you break the oxygen-oxygen bond. And then you're going to ionize. When you're going to ionize, ionization will also happen in 2 steps. Ionization would involve the first ionization energies of the metal. So it's going to involve the ionization of the metal plus the electron affinity of the non-metal, because that would be gaining electrons. So it would electron affinity of non-metal. Okay, so every time, this is what your Bohr cycle is. And one path is equal to the other path. Usually the Bohr cycle is used to calculate the lattice energy. And you can apply the Hess law. Hess law states that one path is the same, it's equivalent to the other path, and you can sum up the values. And if one of them is missing, you can find that missing value. So that is
Electron affinity हमेशा non-metals के लिए होती है ना?
Because they always gain electrons. So you're not going to use ionization energies for them. Okay? And you can make Bohr cycles for pretty much any substance, like as long as it's ionic. Like if I want to make it for Al2O3, it would be Al, the elements, enthalpy of formation, turning it into Al2O3. This is going to be 3/2. 2 aluminiums, this is solid, this is gaseous molecule, and this is a solid ionic lattice. That's delta HF. First step, atomize. So you're going to make Al gaseous atoms and 3 oxygen gaseous atoms. How do you do that? That would be enthalpy change. So that's atomization. That would be 2 steps, basically. It would be the enthalpy of atomization of Al. And that's going to be multiplied by 2, plus it would be you're breaking the oxygen-oxygen bonds, and you'll be breaking 3/2 of them. The bond energy. That's what you're doing. Once you've done that, you're going to ionize them. You're going to ionize them. 2 aluminium 3+ ions would be formed in gaseous state. 3 oxygen ions would be formed in gaseous state. So how do you ionize them? It would be the first plus second plus third ionization energy of Al into 2, because aluminium is supposed to lose 2 electrons, and you've got 2 aluminiums. Oxygen forms a -2 ion, so it's the electron affinity of oxygen plus electron affinity of oxygen -1. Remember, 2 electrons would be gained. Oxygen will first turn into oxygen -1, then oxygen -1 will turn into oxygen -2. And there are 3 oxygens, so this will happen to all 3 of them. And that's the last step. That's this one is my lattice energy. So anyways, coming back to the question. Clear, Ibrahim? Is this clear?
And
did anyone calculate this? What do you get for this?
1477.
Okay, so we got 14. So we found W. We got 1477. And now we can find this X. Okay, I think in the next step he's asking for the enthalpy change Z. Z is this one. So now we know that one path is equal to the other path. So W is basically equal to this other path. W goes from this point to this point. So we're going to go from this point to this point. So we know that 1477 is equal to, what is X? That's -795. That's already given. And then it's -83. Be careful with the arrow directions. And then this one changes. The direction of this arrow changes. What is Z? Z is I mean, let me just be very careful. Is the arrow direction changing or not? So it is the enthalpy of hydration of Cl ions, Cl gaseous ions turning into aqueous ions. So the arrow is in this direction. If I go in the opposite direction, the signs are going to change. This would become plus and this one would become minus. So it's going to be plus 364 into 2 and minus x. Okay, I'm going in the opposite direction. And now I have to find what x is. So be careful with the sign. The z sign has to change. It has to be flipped around. So what do we get for x? Saim, we got the anyone can even do this.
Sir, I'm getting negative 1627.
So you're getting that's for x negative
27.
I said now they weren't really interested in x. The question was actually about z. So what was z? Z was equivalent to minus 364 into 2. So z was minus 364 into 2. 364 into 2. And plus x. And x comes out to be minus 1627. So what do we get for this?
Negative 2355.
So we're getting negative 2355. So z is negative 2355. Now, for questions like these, and let me open the market scheme. Questions where there's a lot of addition and subtraction, there's a very high probability of getting the answer wrong. So let's open.
Sir, I've been checking the answers. They're correct.
Correct. So here, that's good. I mean, but remember, be very careful when you have so many addition and subtraction. It's very easy to get one sign wrong, at least. And then he's asking for the value of the hydration of calcium ions. We already figured that out. We already figured out x. That was the missing thing. We've already done that. So x is minus 1627. That's already done. Okay, so that part of the question is, I think done. So just remember, okay, they were looking for z, and before that they were asking you to calculate w. So we did calculate w. W was calcium solid turning into calcium gaseous ions and Cl2 gas turning into.
Sir, we had to calculate z, right? So we could just use w, x, and y. Why did we like do whatever was inside z? Why did we bring that all into?
No, we did. We just changed the steps. Okay, what we just did was we found x first and then we found z.
Oh yeah, okay.
The question was actually looking for z and then they were looking for x. So it's kind of the same thing. You would still do the same amount of math for this. Okay. So anyway, so basically we got this step first, where they wanted us to calculate the enthalpy change of hydration of calcium ions, which was x. So I'll just quickly go over this. This was gaseous ions turning into aqueous ions. So that was hydration of calcium ions. Cl ions turning into aqueous ions. That was the hydration of Cl ions. And they had given us the hydration of Cl ions, but not the hydration of calcium ions. That was x. W we had to calculate separately, and we did that. And the rest was basic math, basic Hess law. TK, clear? Is this clear to everyone?
Yes, sir.
So now next one. Write an expression in terms of W, X, Y, and Z to show how the enthalpy change of two transformation can be used to calculate the lattice energy of calcium chloride. The lattice energy of calcium chloride. Do we have lattice energy over here? I don't think we do. So now I think this Hess cycle would be helpful. because we did draw the Bondable cycle. So let me refer back to this. So if you look at this Bondable cycle, what is lattice energy equivalent to? Like if I make the two parts, this is lattice energy. What's the other path? The other path is this one, right? So lattice energy is equivalent to minus W. This is minus W, right? Plus, I think delta HF. Is this clear? Lattice energy is equal to minus W plus delta HF. You clear?
Yes, sir.
Okay, because we did draw this earlier. So lattice energy is minus W plus plus delta HF. But what they are saying is, okay, we have to write an expression in terms of W, X, Y, and or Z. And or Z to show how the enthalpy changes of two of the transformation can be used to calculate the lattice energy of CaCl2. So two of the transformations can be used to calculate, so we can do that over here. I think, do we have lattice?
Sir, X or Z में क्या फर्क? I mean, Z is the same value but in opposite direction. So, I mean, you would just change the sign of the Z.
X and Z?
और आपने वहाँ पे you took, yeah, this.
X and Z are not the same thing. W plus X plus Y is the same as Z. But okay, not even that, because the arrows are in different directions. This is what you're saying. Now, two paths are the same, right? So this is what you're saying. This is one path, right? And that's my other path, right? Ye keh rahe ho na? And they should be equal, right?
जी के मतलब Z is downwards or X
No, I'll talk about
so that makes X and Z equal लेकिन सिर्फ sign का difference.
X and Z are not equal. X is from this point to this point only. These two arrows are equal. Because they start at the bottom, they start at calcium chloride aqueous and they reach all the way to the top. Is that clear?
जी. And I mean, where does X start and where does X? अच्छा, X is.
यहाँ से start हो रहा है ना X.
नहीं, आपने जो X बनाया है कि ये 364 into 2 minus X.
नहीं वो तो that was the unknown X. That was the small X. It wasn't this one. That was the unknown hydration of calcium ions. Well, I was trying to figure out what Z was, right? So Z was Cl-1 gaseous turning into aqueous Cl ions, right? So that was the enthalpy of hydration of Cl ions. What was missing was calcium ions turning into calcium aqueous. That was missing. Enthalpy of hydration of calcium ions was missing, and that I took as X. So this is not that X. Okay, is that clear?
Yeah.
Achha, another thing is in the same diagram, this one, let's stick to this one. What do you think is lattice energy? From which point to which point? What is lattice energy?
Z minus Y.
Z minus. Okay, lattice energy is gaseous ions turning into solid ionic lattice. So lattice energy is from gaseous ions to solid ionic lattice. So that is lattice energy. So it's either minus W plus X, like you have to go, I mean, if you follow this arrow, it's going to be minus W plus X. So lattice energy will have two values. It's either going to be minus W plus X. That's one way. You have that's your starting point. This is your end point. And there are two routes which you could take. The other route is you can go from this direction and you can go all the way till this point. You can remember there are two paths. Either you can go directly. So that would be you start from this point, you reach this point. That's minus W plus X. Or you can follow the other path. The other path would be Z. And Y, you have to go in the opposite direction. So it's going to be Z minus Z minus Y. Is that clear?
Yes, sir.
Yes, sir.
Okay, so lattice energy is gaseous ions turning into solid ionic lattice. This is your starting point, this is your end point, and there are two ways of getting there. One is you can go directly to that. The other one is you can go all the way, make this first, and then go back and form this. Okay. So that's so there are two expressions actually, minus W plus X or Z minus Y. So minus is quite hard there. So this one, we have two expressions, minus W plus X, or it could be Z minus Y. Now state, so is you clear? Is this clear? Right? Sign clear?
Yes, sir.
Okay. State whether the lattice energy of CaCl2 is more or less exothermic than the lattice energy of MgF2. So calcium and Cl2 and Mg and F2, who makes a stronger lattice and why? Like when do you have a stronger lattice?
When the ionic charge is greater.
He gets so greater charge, that's one, and smaller radius as well. So greater charge is one factor, but that is not a factor over here. Because the charge is the same. +2 Mg is also +2. Cl is -1, F is also -1. So charge is really not a factor. It's basically the size of the ion. Smaller ions, they would be closer together. They will have more charge density and there will be more attraction between them. Smaller ions have greater. So which one has a smaller ion?
Magnesium.
And fluorine as well. Both of them are smaller compared to calcium. And so that means the lattice energy of this thing would be more exothermic. It's going to be more exothermic. Okay, is that clear? Okay, remember there are two factors, number one, number two. Okay, that determine the strength of the ionic lattice. Ionic lattice is something like this. It's a lattice of oppositely charged ions all attracting each other. Okay. So when do ions really strongly attract each other? That's number one. You've got greater charge, but that's not a factor here. Number two is smaller ions. They always have stronger attraction. Okay, clear? It's just a 1 mark question. So you have to mention this one. The sulfates of group 2 elements vary in solubility down group 2, give names of two solutions that could be mixed to form barium sulfate. So that's ionic precipitation. You can use barium nitrate, aqueous. Nitrates are all soluble and mix it with any sulfate. Sodium sulfate would be helpful. A soluble sulfate. If you mix them together, they're going to form a precipitate of barium sulfate, which is a solid. And what's going to be left in the solution is going to be sodium nitrate, which is going to be aqueous. Why does ionic precipitation happen? Ionic precipitation happens when you mix two soluble substances. So in your beaker, you'll have barium ions, you'll have nitrate ions, and you will have sodium ions, and you'll also have sulfate ions. They all get mixed together and they don't have any reactions. Nitrates and sulfates, they don't react with each other. What will happen is that the ions would randomly combine, and barium ions and sulfate ions, they form an insoluble solid because they're insoluble. So the solution will not have barium sulfate solid. The solution will only have sodium nitrate aqueous ions. Why? Because they're soluble. Group 1 compounds are all soluble. Nitrates are all soluble. So that is what ionic precipitation is. Now he's saying, and this is a typical question, it's a typical 4-mark question. Why do the solubilities of the sulfates of group 2 elements vary down the group? So why do they vary down the group when you try to dissolve them? So just drawing this is the enthalpy of solution. This is what happens when you dissolve a sulfate. It dissociates and mixes with aqueous ions and turns into aqueous ions. There are two steps when you want to dissolve a salt. Like if I have NaCl, the first thing is I would have to break the lattice. If I want to scatter the ions in water, the first thing is I would have to break the lattice. I would have to turn the magnesium ions and the sulfate ions into gaseous ions. So I'm going to break the lattice. That's the negative of lattice energy. That's the opposite of forming the lattice. Once the lattice has been broken, I'm going to mix or scatter the ions in water, and they're going to form bonds with water, and they'll be surrounded by water, and that's enthalpy of hydration of the same ions. So solution mixing or dissolving something in solution requires two things. First is break the lattice, ionic lattice. ठीक है, उसको तस्वीरों में ना इस तरह होगा कि ionic substance, if it's dissolving, it's going to look something like this. Like this. First thing is the ions are all sticking together. So the first step would be you would break the lattice so that the ions get scattered. Once the ions get scattered, they're going to be surrounded by water molecules. That's enthalpy change of hydration. So that's how ionic substances, they mix with water and they form complex ions. Transition metals, they end up forming complex ions. So this is what's going to happen. So these are the two steps. So the first part is what is happening to the solubility of sulfates of the group 2 elements vary down the group. They become less soluble. So group 2 sulfates, and it's a typical question, so it's better, you're better off memorizing this. So group 2 sulfates solubility decreases down the group. That's the first statement, 1 mark. If they haven't told you already in this question, then that's 1 mark. So why does it decrease down the group? The reason it decreases is down the group ionic radius increases. The ions become bigger. So the ionic radius increases. So the bonds that are being formed and the bonds that are being broken, like you're breaking the lattice and you're forming bonds, they'll all be weak. Bigger ions, they always make weaker bonds. So both lattice energy and enthalpy change of hydration, they decrease. I said both of them, they decrease. Because bigger ions, they're going to form weak bonds. So the lattice would be weaker and the bonds that are formed with water would also be weak. But one of the part is endothermic. You're breaking the lattice. The second is making bonds with water. That's exothermic. So if the solubility down the group decreases, that means the overall process is becoming more endothermic, which is why it's not happening. It requires energy. So that means the endothermic part decreases less compared to the exothermic part. So both of them are decreasing, but the lattice energy decreases less compared to enthalpy change of hydration. So which means this is big and this is, relatively speaking, small. The endothermic part is bigger and the exothermic part is smaller, which is why the overall thing would become more endothermic. Hence, enthalpy of solution becomes more endothermic. So remember, this is a very typical question, and that's your 4 marks. About group 2 sulfates, the solubility decreases down the group. Why does it decrease? Because dissolving a substance requires two things. You're going to break the lattice, you're going to scatter the ions. Once the ions are scattered in water, the ions will be surrounded by water molecules. They're going to form bonds with water molecules and they would become hydrated aqueous ions. So breaking the lattice is an endothermic process. You're breaking bonds. Forming the aqueous ions, that's a exothermic process because you're forming bonds. the ions, gaseous ions, when they break off, they're going to mix with water molecules and they're going to form bonds. So one part is endothermic, the other part is exothermic. So the overall enthalpy of solution depends on two things. One is endo and the other one is exo. So if the solubility is decreasing, that means enthalpy of solution is becoming more and more endothermic. So down the group, this part is becoming bigger and this part is becoming smaller. Even though both of them are decreasing, because down the group ionic radius increases. So you have bigger ions down the group. Both lattice energy and enthalpy of hydration decrease. But relatively speaking, this is still bigger and that is still smaller. So lattice energy decreases less compared to enthalpy change of hydration, which makes it more not exothermic, endothermic.
Sir, what was hydration? I mean, which part of this reaction was hydration?
This part, gaseous ions turning into aqueous ions.
अच्छा ठीक है.
अच्छा फिर ये कि so that question is over. We're on the fourth question now. So remember, make sure you revise this and make sure there's another question which is exactly the same, which is on hydroxides. So down the group, the solubility of the hydroxides increases. Everything is the same, but the solubility of the hydroxide increases. That means yahan tak everything remains exactly the same. Down the group, ionic radius increases. So both these values are decreasing. But in that case, this part is bigger and that part is smaller, and the enthalpy of solution is becoming less endothermic or more exothermic. So that is exactly the opposite of this. So make sure this is a very typical, it comes in almost every paper. It's a typical 4-mark question that almost comes in every paper. So make sure you remember that. Chalo, let's continue with the same paper tomorrow then.
Chalo, okay, sir. Allah Hafiz.
Chalo.
Thank you, sir. Allah Hafiz, sir.
Okay, everyone, take care.
Allah
Hafiz.
Thank you, sir.
Okay, Munir, take care.
Thank you.